There's a moment just before a strike when nothing looks like it's about to happen. A leaf holds still. The air between flowers is empty and warm. Then something moves. A shadow that wasn't a shadow, a stillness that was actually a coil. And whatever had been alive a half second ago is no longer making decisions. At insect scale, the interval between safe and gone is so brief it barely registers as time at all. There's no cry, no chase, no drama visible to us. Just the quiet resumption of stillness and one less set of wings in the air. What makes this hard to grasp, watching from human height, is how much of it runs on precision rather than power. These aren't battles of endurance or strength, they're solved problems. Millions of years of pressure, predator and prey locked in the same arms race, generation after generation, have produced nervous systems that can process, decide, and act faster than a human blink. A mantis doesn't lunge and hope. A robber fly doesn't chase. The strike, when it comes, is the end of a calculation that began the moment the target appeared, and it's already over before the prey's own nervous system can file a complaint. This is the world the camera tries to follow, and often can't. Unfolding in the gap between grass stems, in the shadow under bark, in the half-inch of airspace above still water. It doesn't announce itself. Size means less here than timing. Strength matters less than the ability to act inside the narrow window before escape becomes possible. Some animals survive by being fast. Others survive by making themselves the thing that something fast never sees coming. Both strategies have been refined into something close to art. If art were measured not by beauty, but by whether you were still alive when morning came. What follows is an attempt to sit with that logic for a while, to actually look at what's happening down there, and take it seriously. Look closely at the stem. That shape, the one that seems like an extension of the leaf, angled just slightly wrong for a plant but just right for something waiting. That's the mantis. It isn't crouching in the way a cat crouches, with visible tension and intent. It looks genuinely botanical. Its thorax a narrow green twig, its folded forelegs tucked under its head as though in some kind of repose. Other predators commit to movement. The chase, the patrol, the ambush that requires closing distance. The mantis has made a different deal with the physics of hunting. It removes itself from the equation entirely and lets prey walk into range on its own schedule. Somewhere in the grass below, a grasshopper is climbing a stem, testing the air. It has no idea that the shape it's approaching has already noticed it. What allows this strategy to work is a combination of adaptations that don't individually seem remarkable, but together produce something close to a perfect trap. The mantis has large, forward-facing compound eyes that give it something most insects lack: genuine depth perception. At this scale, a few centimeters is the difference between a successful strike and empty air, and the mantis needs to know not just where the prey is, but whether it has crossed into the zone where escape becomes functionally impossible. Until that threshold, the mantis holds. It doesn't flinch. Some species add a further layer of deception with a slow, rhythmic sway, a subtle rocking that mimics vegetation moving in a light breeze, making the disguise dynamic without compromising it. The patience isn't incidental. It's load-bearing. Then everything happens at once. The raptorial forelegs snap forward from their folded position in a strike that takes roughly 50 to 70 milliseconds. Fast enough that the prey's escape reflex, even if triggered, simply doesn't have time to finish its own sentence. Those forelegs aren't just fast. They're purpose-built, hinged, lined with interlocking spines, shaped to close around a body and hold it regardless of how hard it struggles. A fly may detect the air displacement. A grasshopper may begin to push off the stem. It doesn't matter. The mantis has already crossed the distance before those signals complete the journey from sensory organ to muscle. The prey's last mistake wasn't being slow. It was being close. There's something almost counterintuitive about the mantis as a predator, which is part of what makes it such a good opening to this subject. For most of its hunt, it looks like the least dangerous thing in the meadow. Stationary, serene, apparently indifferent. The violence, when it arrives, seems to come from nowhere, because nowhere is exactly where the mantis has been. What it represents is a principle that runs through insect predation more broadly. Energy spent waiting can be worth far more than energy spent searching, provided your disguise holds and your strike is fast enough to close the deal. In an environment where moving exposes you to your own predators, stillness is both camouflage and conservation. Afterward, the meadow doesn't react. That's the thing that stays with you, watching this. The mantis feeds with the same composure it hunted with, gripping its prey in those spined forelegs, while the grass around it continues its ordinary business. Other insects moving through stems, leaves catching light, the whole system ticking along as if nothing happened. Which, from the meadow's perspective, nothing did. One grasshopper less. One mantis fed. The transaction was over before it registered as an event. That's the first lesson this place offers. The most effective predators here aren't necessarily the strongest or the fastest in open pursuit. They're the ones that make the distance between living and not living as short and as invisible as possible. If you've ever had a jumping spider turn to face you, really face you, rotating its whole body with that slightly unnerving attentiveness, you already know there's something different going on here. Most insects register your presence as a change in light or vibration. The jumping spider looks at you. Those two large front eyes, disproportionate and almost cartoonishly prominent, are not simple motion detectors. They're long focus lenses, capable of resolving detail and assessing depth with a level of accuracy that seems to belong to a much larger animal. This is a spider that hunts the way a hawk hunts, by seeing the problem clearly before committing to a solution. That visual system shapes everything about how it operates. Where a mantis commits to one patch of vegetation and waits, the jumping spider covers ground: bark, leaf surfaces, stone walls, flower heads, window ledges. Open terrain with prey that can flee in any direction. A fly can lift off. A moth can slip behind a stem. The spider's answer to this is not speed alone, but precision that comes before speed. When it locates a target, it orients toward it in a series of small, deliberate adjustments, tilting, stepping sideways, narrowing the angle. Watching this, it's hard not to read intention into it, even knowing you're projecting. But the behavior really does resemble problem solving. The spider is reducing the geometry of the attack, finding the line its body will need to travel, and waiting until the variables resolve into something it can act on with confidence. The jump itself runs on an unusual mechanism. Jumping spiders don't rely purely on muscle contraction the way a grasshopper does. They alter hydraulic pressure inside their legs, forcing fluid into the limbs rapidly enough to produce an explosive extension, essentially using their own circulatory system as a catapult. Before launching, the spider anchors a silk line behind it, not to trap anything, but as a tether for itself. If the surface shifts, if the target moves at the last instant, if the landing goes wrong, there's a line back. It's a detail that tends to get overlooked in favor of the drama of the leap, but it says something worth noting about how evolution actually works. Even a system built around explosive commitment has a contingency built in. When the jump comes, it happens in one uninterrupted motion: launch, flight, contact. And the spider arrives with its forelegs and fangs already in position. There's no secondary lunge, no scramble to reorient. The landing is the capture. Venom works quickly from there, and the prey's struggle, if there is one, is brief. From a distance, it looks instantaneous, and in terms of elapsed time, it nearly is. But the preparation, the watching, the angling, the quiet hydraulic loading of the legs, that was the real hunt. The jump was just the punctuation. What the jumping spider adds to this series, after the mantis, is a different answer to the same pressure. How do you catch something that can escape in any direction, in open space, with no structural advantage to hide behind? The mantis solves it with concealment and proximity. The jumping spider solves it with information, gathering enough of it, through those extraordinary eyes, that by the time it moves, uncertainty has already been reduced to an acceptable margin. There's almost something methodical about it. And then suddenly there isn't. And that transition from patient observation to committed violence is as clean and decisive as anything in the insect world. The leaf it hunts on keeps moving in whatever breeze is passing through. Other insects cross the same surface, and the spider tracks them with that characteristic head turn, assessing, deciding whether to pursue or let them go. It doesn't strike at everything. Selectivity is part of the strategy. A failed jump costs energy and risks exposure. So it waits for the geometry to be right, for the distance to be manageable, for the angle to favor arrival over escape. And when all of that aligns, the space between the spider and its prey, which had looked like ordinary air, closes in a fraction of a second and turns out to have been a trap all along. There's a web stretched between two grass stems at the edge of the meadow, and if the light isn't hitting it at the right angle, you won't see it at all. That's partly the point. The wasp spider, boldly striped in yellow, black and cream, one of the most visually striking spiders in European grasslands, sits at the center of a structure that has already done most of the hunting before anything has been caught. This is a different philosophy from the mantis or the jumping spider. Those predators carry their weapons in their bodies. The wasp spider has externalized its trap, suspended it in the air between stems, and is now simply waiting for the meadow's ordinary traffic to make a mistake. The web is more sophisticated than it looks. An orb web isn't just a net. It's a layered system where different threads serve different functions. The frame lines hold the structure rigid. The spiral threads are coated in sticky droplets that catch and grip. And running beneath it all is something less visible but arguably more important: the web's sensitivity to vibration. When a grasshopper or bee or fly hits the silk, the impact travels through the structure almost instantly, and the spider, legs resting on the threads at the hub, feels the information arrive before it sees anything. Weight, direction, intensity, the frantic pattern of something struggling versus the dull tremor of a seed brushing a strand. The spider reads all of it through its legs. The silk is, in a very real sense, an extension of its nervous system, stretched across open air to cover ground its body never has to cross. What happens to the prey in those first moments of contact is worth considering. A grasshopper that clips the web mid-jump doesn't just get stuck, it gets disoriented. Its wings, which are its fastest route to escape, become liabilities, catching more silk with every beat. Its legs, which might push it free, pull threads tighter with each kick. The physics of the trap are almost cruelly well designed. The behaviors that would save the insect in open air are exactly the behaviors that make things worse here. By the time the spider is moving toward it along the non-sticky radial lines, using the web's own architecture as a roadway, the prey has already spent much of what it had. The spider arrives fast, but this isn't the speed of pursuit, it's the speed of completion. The first thing it often does is wrap, pulling silk from its spinnerets and binding the prey in rapid rotations before delivering venom. This sequence matters. A large grasshopper or a wasp, handled carelessly, can injure a spider. The wrapping reduces that risk by neutralizing the prey's movement before close contact becomes necessary. It's a kind of operational caution built into the kill. Subdue first, then bite, then wait for the venom to finish the immobilization and begin breaking down tissue for digestion. The whole thing is fast, but it unfolds in stages, each one narrowing the prey's remaining options. Stepping back from the specifics, there's something genuinely interesting about what the wasp spider represents in the broader logic of predation. The mantis and the jumping spider both solve the problem of catching fast-moving prey by being faster, sharper, more precisely timed. The wasp spider solves it by making speed almost irrelevant to the first phase of the hunt. It builds the trap in advance, in a location chosen for traffic, low across the grassland where jumping insects travel, often with a stabilimentum, a zigzag band of thicker silk woven into the web whose exact function is still debated, but which may help camouflage the structure or make it visible enough to prevent larger animals from walking through it. The spider invests in infrastructure rather than athleticism, and in a warm meadow full of insects moving between flowers and stems, that investment pays. From a distance, the scene is almost serene. A patterned spider on a geometric web, grass moving slowly in the heat, light catching the silk for just a moment before the angle shifts and it disappears again. It doesn't look like violence, it looks like lace. But somewhere in that structure, the tension is already loaded. And whatever flies through that particular column of air in the next few minutes will discover with very little warning that the empty space it was crossing had already been claimed. Somewhere between two branches at the forest edge, where the canopy thins and insects move freely through shafts of warm light, there is a web you won't see until you're almost in it. The golden silk Orb-Weaver builds large. Spans of 1 meter or more are not unusual. And it positions its trap across the natural corridors that flying insects use. Gaps between shrubs, clearings between trees, the open air above a path. The silk has a faint yellowish sheen that catches the light at certain angles and disappears at others, which means that a beetle or moth crossing at speed has very little chance of seeing it in time. This isn't an ambush in the traditional sense. The spider doesn't chase. It doesn't approach. It simply places the trap where flight already happens and waits for the forest's own traffic to do the work. What makes this strategy so effective is a quirk of physics that works entirely against the prey. A flying insect carries momentum, and when it hits the web, that momentum doesn't stop. It continues driving the body deeper into the silk. Wings that beat to pull free make contact with more threads. Legs that kick for purchase snag on the spiral. The faster the insect was traveling when it hit, the more comprehensively it tends to become entangled. Speed, which is usually the escape mechanism, becomes the mechanism of capture. The web doesn't need to overpower the prey. It just needs to redirect what the prey was already doing. The spider itself waits near the hub, or sometimes in a separate retreat connected to the web by a signal line, with legs resting on the silk so that vibration travels directly into its body. It's worth pausing on how much information arrives through this system. A leaf brushing a thread produces a brief, decaying tremor. Wind loading shifts the whole structure uniformly. But a living animal struggling in the spiral creates something different. An urgent, irregular, repeating signal that the spider's nervous system has been shaped by selection to recognize immediately. The web effectively extends the spider's senses across a wide hunting area, meaning it can monitor a large space in the forest while expending almost no energy. It's a remarkably low-cost way to run a high-yield operation. When the spider moves, it moves with purpose. The orb web has two kinds of thread: the dry, non-sticky radial lines that run like spokes from the center, and the sticky spiral that catches prey. And the spider knows exactly which is which, moving along the safe lines with the ease of an animal navigating its own house. By the time it reaches the impact site, the prey is usually already compromised, tangled, exhausted from struggling, wings gummed. The spider's next steps, biting, wrapping, repositioning based on the size and threat level of the catch, follow a sequence that's been refined across millions of generations, and it shows. There's very little fumbling. A wasp gets wrapped more thoroughly before the bite. A soft-bodied fly gets bitten quickly. The spider adjusts. There's an uncomfortable elegance to this kind of predation, and it's worth naming it. A moth that evolved to navigate darkness with extraordinary sensitivity. A fly capable of evasive maneuvers that outperform most engineered aircraft. A wasp carrying venom of its own. All of them can be defeated not because they were outmatched in their specialty, but because their specialty was irrelevant the moment they hit the silk. The golden silk Orb-Weaver doesn't compete with its prey on their own terms. It builds a system that makes their terms not apply. In that sense, it's less like a predator and more like a strategist. And the forest, with its constant movement of insects through predictable corridors, keeps feeding the strategy for free. The web catches the light again for a moment, that brief gold flash that gives the species its name. And then the angle shifts, and it's gone. The forest continues around it, leaves turning in a faint breeze, insects drifting through the understory, the ordinary business of a warm afternoon. The spider hasn't moved. It doesn't need to. Somewhere in the next few minutes, or the next hour, something with wings will cross that stretch of air at full speed, as it has done 1,000 times before, and find that this particular gap between the trees is no longer empty. The trap was already there. It's been there all morning.
After dark, the ground changes. The stones that absorbed heat all day release it slowly, and the dry soil breathes out warmth into cooler air,
and the whole surface of the earth, at ground level where it actually matters, becomes a different kind of place. Beetles push through loose grit. Crickets move between rocks with their antennae reading the air. Roaches track the edges of stones and roots, staying close to cover the way animals do when they know, without knowing it, that open ground is a gamble. In a crack between rocks, at the mouth of a shallow burrow, or pressed flat beneath a stone still warm from the afternoon, the black scorpion waits. It isn't resting, it's positioned. The scorpion's primary senses have almost nothing to do with vision, which is worth sitting with for a moment. In the dark, that might seem like a liability. It isn't. Across the legs and body are fine sensory hairs and specialized slit organs that detect vibrations traveling through the ground. The scrape of a beetle's legs on grit, the irregular push of a cricket moving between stones, the subtle surface pressure of something approaching from a few centimeters away. These signals carry direction and distance. The scorpion doesn't need to see its prey to know where it is and how fast it's moving. It reads the ground the way something with much better eyes might read a lit room, and in total darkness, that's an enormous advantage over almost everything sharing the same terrain. What happens when prey comes within range is not complicated, but it is overwhelming. The pincers move first, closing around legs, a wing case, or the body itself with enough grip to stop the prey from maneuvering its own defenses into position. For softer or smaller prey, that grip may be sufficient on its own. For something larger, more dangerous, or harder to hold, the tail comes forward and the sting is applied with a precision that looks almost clinical. The venom targets the nervous system, and the effect is rapid. Coordinated movement collapses, the struggle becomes erratic and then fades, and the scorpion settles into feeding. Every part of the animal has a defined role in the sequence: detect, close, restrain, sting, hold, and they work together in a way that leaves very little space for the prey to find an exit. A beetle can twist against its own armor, trying to lever itself free. A cricket can kick with surprising force. A roach, flattened and strong, may try to use its body shape to push into the ground and slip the grip. The scorpion's answer to all of this is structural: a low center of gravity, a heavily armored body, and pincers designed not just to grab, but to maintain control under resistance. The struggle stays contained. This matters because a prolonged fight is dangerous for both parties. A large cricket or beetle that gets enough leverage can cause real damage. So the goal isn't a drawn-out contest, but a rapid reduction of the prey's ability to make the situation worse. The sting is the shortcut to that outcome. There's a broader logic to how the scorpion lives that explains the intensity of the kill. Many scorpion species occupy environments where food is genuinely unpredictable, and conditions can shift from tolerable to punishing within hours. They've responded to this by evolving a metabolism that can run extraordinarily slow when necessary. Some species can survive on a fraction of the food intake that would sustain a similarly sized animal of most other groups. They reduce activity during the harshest periods and emerge when prey is moving and temperatures are manageable. All of which means that when a hunting opportunity does arrive, after potentially a very long wait, a failed or incomplete kill isn't just an inconvenience. It's a significant cost. The violence of the attack is, in part, a response to the scarcity of the environment that shaped it. Watching a scorpion hunt, if you can manage it in near darkness, with a UV light, which makes them glow a faint blue-green in one of nature's stranger optical details, what strikes you is how little wasted motion there is. No rushing, no pursuit across open ground, no second attempt after a miss. The scorpion waits until the geometry is right, until the prey is close enough that the outcome of engagement is not really in question, and then it acts with a completeness that's almost final-looking. After the previous chapters, the mantis in its meadow, the jumping spider on its leaf, the Orb-Weaver's suspended geometry, the scorpion feels like a different register entirely. Not aerial, not visual, not architectural, just ground level, tactile, and certain. A shadow under a warm stone, reading the earth for footsteps, waiting for something to make the last small mistake of its evening. The pond edge in late morning is one of those places that looks, from any reasonable distance, like pure tranquility. Light breaks across the water. Reeds shift in whatever faint breeze is moving through. Small insects rise from the surface in loose drifts, catching the light for a moment before disappearing against the reflections. And through all of it, the Scarlet Dragonfly moves. A streak of red that patrols this airspace with a focus that has nothing to do with the calm it appears to inhabit. It is the most capable aerial predator at this scale, and almost everything sharing this warm column of air above the water is potential prey. The eyes are where this starts. A dragonfly's compound eyes are among the most developed of any insect, wrapping around most of the head and giving it close to 360-degree vision with a forward zone of particularly sharp focus. But what makes them remarkable isn't just the field of view, it's the processing speed. A small midge changing direction above the reeds, a mosquito drifting through a shaft of light, a fly cutting an erratic line over the water. To most predators, these would be nearly impossible targets, too fast and too unpredictable to track reliably. The dragonfly doesn't track them in the way a cat follows a moving object, reacting to where the prey is. It predicts where the prey is going, calculates an interception point in three-dimensional space, and flies to meet it there. The prey, in a very real sense, is already caught before the dragonfly has closed the distance. Making that interception possible is a flight system unlike anything else in the insect world. Most flying insects move their wings in linked pairs, which limits how quickly they can change direction or adjust their angle of attack. Dragonflies control each of their four wings with independent muscles, which means they can hover, fly backward, make sharp lateral shifts, and accelerate from a near standstill in ways that would simply be impossible with a more conventional setup. Watch one patrol a pond territory, and you'll see this in action. A hovering pause, a sudden pivot, an explosive burst forward. And what looks fluid and almost casual is actually continuous high-speed adjustment. The legs, meanwhile, are held forward in flight in a configuration that forms a catching basket, angled and spined, designed not for ground contact, but for closing around a small body moving through air. When the dragonfly arrives at its interception point, the legs do the catching and the mandibles begin feeding, sometimes while the dragonfly is still in flight. The whole sequence, acquisition, interception, capture, can take under a second from the moment of commitment. The success rate is what stops you when you first encounter the numbers. Studies on dragonfly hunting have recorded capture success rates above 90% in some species, which is extraordinary for any predator. Most large, celebrated hunters, lions, sharks, even falcons, succeed on a fraction of their attempts. Dragonflies close nearly every hunt they commit to, which reflects not just speed, but the quality of the decision-making before the attack. They're selective. They don't chase every target. They assess, choose, and then execute with a precision that has very few failures built into it. What's striking about the dragonfly, placed alongside the other predators in this series, is that it operates in the environment that seems most hostile to reliable hunting. The scorpion has the ground. The Orb-Weaver has its silk architecture. The Mantis has its stem. The dragonfly has open air, which offers no walls, no structure, nothing to corner prey against, no physical constraint to use as an advantage. Everything is moving. Every escape route is open in 3 dimensions. And yet the dragonfly has turned this into the most efficient hunting arena of all by developing the sensory and mechanical tools to make open space into something it navigates better than anything else flying through it. The pond continues its afternoon business around all of this. Insects keep emerging from the water, keep drifting upward into the warm air, keep moving between reeds on routes that have nothing to do with the red shape patrolling overhead. That's the nature of this kind of predation. It doesn't disrupt the scene. It just quietly removes individuals from it, one precise interception at a time, until the dragonfly has fed and the air above the water looks, to any casual observer, exactly as full and peaceful as it did before. A still pond is one of those places that invites you to stop thinking about danger. Reflected clouds, a few fallen leaves sitting motionless on the surface, the occasional ripple from nothing visible. It has the quality of a pause, something between a mirror and a window, neither fully one thing nor the other. But drop down to the scale of an insect, And that same surface is one of the most unforgiving environments in this whole series of landscapes. Because the water surface isn't just a boundary between air and water. For the wrong animal, it's a trap with no exit. And for the water strider, it's a hunting ground that comes preloaded with a detection system it didn't have to build. The strider's relationship with surface tension is the foundation of everything it does. Water molecules at the surface pull toward each other with enough force to support a small animal, but only if that animal's weight is distributed correctly and its legs don't puncture the film. The strider's legs are covered in thousands of microscopic water-repelling hairs that spread its load across the surface, creating small dimples rather than breaking through. The result is an insect that sits on top of the pond as if the water were a taut fabric, which in a physical sense it essentially is. Its middle legs do most of the propulsion, pushing backward in rowing strokes to generate forward movement, while the hind legs steer and the front legs are kept free for what they're actually needed for. It doesn't swim, it skates, and it does so with a lightness and speed that most pond inhabitants, weighted down by or submerged in the water, simply cannot match. When something falls onto the surface, a fly that miscalculated, an ant that lost its footing at the pond's edge, a mosquito too weak to lift off, the water doesn't absorb the event quietly. Surface tension transmits it. The struggling insect produces ripples that move outward in patterns, and those patterns carry information. The frequency of the disturbance, its intensity, whether it's repeating or fading. The strider detects these signals through its legs, which rest directly on the surface and pick up the vibrations the way a fingertip reads texture. A raindrop produces a single impact and fades. A seed drifting into the surface barely registers. A trapped insect fighting to free itself sends out something rhythmic and urgent, a repeating signal that reads, to a strider, as unmistakably biological. The pond's surface, in this sense, functions as a living alarm system, and the strider is always listening. The response, when it comes, is fast and direct. The strider orients toward the disturbance and crosses the surface in a series of rapid strokes, covering the distance with an efficiency that looks almost frictionless. There's none of the drama of a chase through three-dimensional space. No banking turn, no vertical drop, no sprint through undergrowth. Just a clean, skimming approach across a reflective surface towards something that has already lost the contest before the predator arrives. Wet wings don't generate clean lift. Small legs find no purchase on water. The insect's own attempts to free itself keep broadcasting its location and exhausting whatever it had left. By the time the strider makes contact, the prey isn't so much being caught as collected. The actual kill is quick. The strider grips the prey with its front legs and drives in its piercing mouthparts. It's a true bug, feeding through a specialized beak rather than biting in the conventional sense, injecting saliva that begins to immobilize and break down tissue, then drawing the contents back out. It's not a violent-looking process from any distance, but at the scale it's happening, it's precise and final. What's interesting is the division of labor between predator and environment. The water does the first and hardest part of the work, neutralizing the prey's ability to escape, and the strider handles the rest. It's a hunting strategy built on patience and opportunism rather than raw pursuit. But once the surface sends its signal, the opportunism becomes very fast indeed. The reason this chapter feels distinct from the others is the habitat itself. Every predator so far has operated in a space we can intuitively map. Meadow, forest edge, bark, open air. The water surface is something else. A two-dimensional plane that most animals either avoid or fall through, turned by one small insect into a private highway. The strider isn't just tolerating an unusual environment, it's exploiting a physical property of water that its prey can't use and its competitors can't easily access. That's the quiet intelligence of the thing. Not speed alone, not venom, not architecture, but the occupation of a niche so specific that the whole pond becomes, in effect, its territory. Watch a hunting wasp move through vegetation, and your first impression is probably of something restless, even chaotic. That rapid, jerky flight path over stems and leaf surfaces, the constant course corrections, the way it seems to check and dismiss and move on with an impatience that reads almost like anxiety. It isn't. That movement is a search pattern, and it's efficient in the way that systematic coverage of ground is always efficient. The wasp is running a grid over the available hunting territory, and its senses, sharp compound eyes, antennae reading chemical traces in the air, are filtering everything it passes for the specific signals that mean prey is close and exposed. When those signals resolve into a target, the restlessness disappears. What replaces it is very focused and very fast. The difficulty with hunting caterpillars, beetles, flies, and other insects is that many of them are not passive. A caterpillar will thrash. A beetle will clamp down or tuck into its armor. A spider, if the wasp misjudges, can bite back. The wasp's strategy is built almost entirely around denying the prey enough time to deploy any of this. It commits to contact hard and immediately, seizing with legs and mandibles while simultaneously positioning its abdomen for the sting. The flexibility of the wasp's body, that narrow waist, the articulated abdomen that can curve in almost any direction, exists specifically to make this geometry work under chaotic conditions, when the prey is moving and the wasp is moving and everything is happening at once. The sting lands not as a last resort, but as the first move that matters, because what it delivers isn't just pain. It's a targeted disruption of the nervous system. For wasps that hunt to provision a nest, the goal is often paralysis rather than death, keeping the prey alive but immobilized, so it stays fresh as food for developing larvae. This is, depending on your perspective, either a remarkable piece of biological engineering or one of the more unsettling things in this entire series. The wasp isn't just killing something, it's converting a living animal into a preserved food supply with a precision that a needle and the right drug couldn't reliably improve on. The sting goes into specific locations, near nerve ganglia, into joints, in species that have evolved to do this with a consistency that looks, frankly, like knowledge. It isn't knowledge, of course. It's the accumulated result of selection pressure across an enormous span of time. But the outcome is the same. An animal that was struggling moments ago reduced to something still. Placed alongside the other predators in this series, the wasp represents a different solution to the core problem of catching fast, dangerous prey. The mantis waits and strikes at a precise moment when the prey is optimally close. The dragonfly calculates an interception in open air. The Orb-Weaver lets architecture do the first phase of work. The wasp walks directly into the problem and uses chemistry to resolve it before the prey's physical advantages can become relevant. Speed and venom work together here, in a way they don't for most of the others. The speed gets the wasp into contact, and the venom ensures that the quality of that contact overwhelms whatever the prey was about to do next. A strong caterpillar is strong right up until its nervous system starts receiving the wrong signals, and then it isn't. Out in the field, the rest of the scene carries on with complete indifference. Bees are working flowers a few centimeters away. Ants are crossing stems on their own errands. Flies are lifting and landing on sun-warmed leaves. None of this pauses for what the wasp just did. A brief, violent episode in one small patch of green that lasted a few seconds and is already over. That's the rhythm of this place. Constant, parallel, overlapping dramas at scales too small to register from any comfortable distance. The wasp moves on, carrying or leaving its prey depending on what it was hunting for, and the field resumes the appearance of an ordinary summer afternoon, which it was and wasn't simultaneously. Turn a leaf over in a garden in early summer and you may find them there. A cluster of aphids along the midrib, pale and soft-bodied, barely moving. Mouth parts sunk into the plant's tissue drawing out sap. They look almost inert, like tiny green or yellow beads arranged along the veins where the nutrient flow runs richest. The plant, for its part, is being quietly drained. Cell pressure dropping, energy diverted, the slow damage accumulating in ways that won't be obvious until later. Ants sometimes farm these colonies, tending them for the honeydew aphids excrete, and the whole arrangement has a strange, symbiotic quality that almost disguises what it actually is, a slow-motion infestation. Then the ladybug arrives, and the scene changes register entirely. There's a real gap between what ladybugs look like and what they actually are, and it's worth addressing directly. The rounded body, the glossy red shell, the spots. These have made it one of the few insects that people actively like, the one they'll let walk across their hand without flinching. But the coloring is a warning to birds and other predators, not a friendly signal to humans. Many ladybug species can release acrid, toxic fluid from their leg joints when threatened, a defense called reflex bleeding, and the bright pattern advertises this unpleasantness to anything that might otherwise try to eat them. The shell that looks decorative is functional armor. The insect inside it is, in the right context, a highly effective predator. The reputation for gentleness is almost entirely a human projection. In an aphid colony, the ladybug doesn't need to do anything spectacular. The prey is stationary, soft-bodied, densely packed, and nutritionally rich, the opposite of everything that makes hunting difficult. The ladybug moves through the cluster with its head lowered, gripping with its legs, biting and consuming one individual before moving immediately to the next. Aphids have limited options. They can drop from the leaf, which some do, or walk away slowly, which others attempt. But once a ladybug is inside the colony, the response time for most individuals is simply too slow. The predator is already at the next one. There's no dramatic strike, no interception, no venom, just a compact, armored insect working through a food source with a speed and appetite that, when you scale it against the size of the prey, starts to look like something more serious than a garden visit. The larvae are, if anything, more striking than the adults. They look nothing like the polished beetles they'll become. Dark, spiny, vaguely alligator-shaped, moving through aphid clusters, with a directness that makes them effective predators in their own right before they've even reached maturity. A single larva can consume dozens of aphids through its development. An adult can eat hundreds over a season. When you consider that aphids, under favorable conditions, can reproduce without mating and give birth to live young, a process called parthenogenesis, and that a colony can expand at a rate that feels almost exponential, the role of ladybugs as population regulators starts to look less like a garden nicety and more like an actual ecological service. Without predators putting pressure on the reproduction rate, the arithmetic gets out of hand very quickly for the plants hosting them. What this chapter adds to the series is a different kind of speed. Not the single explosive event of a dragonfly interception or a mantis strike, but the cumulative velocity of many small, decisive actions in sequence. The ladybug isn't the fastest predator in this collection by any individual measure, but in the right environment, doing what it was shaped to do, it can dismantle a colony that took days to build in a fraction of that time. That's a different form of efficiency, and arguably a more ecologically significant one. The aphids don't get a cinematic ending. There's no chase, no duel, no moment of obvious danger. There's just the familiar red dome moving steadily through the leaf, the jaws working, and the colony thinning. A quiet and completely ordinary massacre that most people walk past every day without noticing. It would be easy to dismiss the Leopard Lacewing as a closing choice, as if the series is ending on something decorative rather than dangerous. The adult is genuinely beautiful. Translucent wings patterned in fine detail, a light and unhurried presence on a sun-warmed leaf that seems to belong more to the aesthetic side of a garden than to a sequence about predation. There's something almost ironic about ending here, after the dragonfly's aerial precision and the wasp's chemical efficiency and the scorpion reading the earth for footsteps in the dark. The lacewing, resting quietly on a stem, looks like a different category of creature entirely. It isn't. The larval stage is where the lacewing earns its place in this series, and the larvae look almost nothing like the adults. They're small, elongated, armed with curved, hollow jaws that are purpose-built for one thing: piercing soft-bodied prey and extracting the contents. Aphids are the primary target, along with insect eggs, small larvae, and other vulnerable organisms clustered on leaf surfaces and stems. The lacewing larva moves through these concentrations of prey with a directness that the delicate adult gives no hint of, finding, gripping, and feeding with a speed that is less about physical velocity than about the complete absence of hesitation. The prey it targets rarely has the armor, the reaction time, or the space to make escape a realistic option. The larva is specialized for exactly this kind of opportunity, and in the right patch of vegetation, it is extraordinarily effective. The feeding mechanism itself is worth understanding. The jaws don't chew in the conventional sense. They pierce and lock onto the prey, and the larva injects digestive fluids that begin breaking down internal tissue, then draws the liquefied contents back through the same hollow mouthparts. It's a system that turns a soft-bodied aphid into a food source in seconds, leaving behind a husk that some lacewing larvae, in a particularly grim piece of behavior, will actually attach to their own backs as camouflage, carrying the remains of previous meals as a disguise among the colony. That detail, more than anything else, captures how thoroughly the lacewing larva has been shaped for life as a predator inside the very populations it's consuming. One thing this series has tried to establish across 10 very different animals is that speed in predation isn't a single thing. It's a category that contains multitudes. The dragonfly's speed is aerial and mathematical. The mantis's speed is mechanical and compressed. The water strider's speed is reactive, reading the surface for signals. The lacewing larva's speed is something quieter, the speed of finding weakness and acting on it without delay, in an environment where the prey is already gathered, already feeding, already committed to staying in one place. There's no pursuit necessary, there's no trap to build or territory to patrol. There's just a predator that evolved to recognize a specific kind of vulnerability and close the gap before anything changes. What stays with you, thinking about the lacewing as a final chapter, is the gap between appearance and ecological reality, and how that gap runs through this entire subject. Almost nothing in this series looked like what it was from the outside. The mantis looked like a twig. The wasp spider looked like jewelry suspended in the grass. The scorpion looked like a rock. And the lacewing looks like something you'd find pressed in a Victorian botanical illustration. Fragile and lovely and completely unthreatening. The garden above the leaf is peaceful, the light is warm. But on the underside of that leaf, a larva is working through an aphid colony with hollow jaws and no particular hurry, because it doesn't need hurry. It needs only proximity, and the rest follows. That's the note this series ends on. Not a dramatic collision, but a quiet, efficient disappearance in a space so small you'd have to know to look for it.